Okay, good afternoon everyone. Today I'll be discussing about exploring massive neutrino signature in galaxy bispectrum multipole and its detectability aspects in Euclid. This work is mainly done in collaboration with Devanjan Sarkar, Ikmo Samonto and Professor Suprik Pal. So here is a brief outline of my talk. First I will discuss about the impact of massive neutrino in power spectrum as well as bispectrum, basically in matter power spectrum. And as we know that, and then I will discuss about the galaxy bispectrum multipoles and whether the effects of neutrino mass and galaxy bias in the galaxy bispectrum multipoles, and analyze the galaxy bispectrum multipoles in a spherical harmonics basis and try to observe whether try to explain whether Euclid can detect this nucleus signature in these multipoles. So, okay, first of all, why going beyond power spectrum? And that is already previously discussed in previous session that to extract information for power spectrum for higher k, we need to go to higher loop corrections. But in the bispectrum, we can get information in the tree level where there is mode mixing. So in that sense, another thing that you can also break degeneracies between cosmological parameter like F sigma 8 and also galaxy bias and neutrino masses. So first let me discuss about the impact of massive neutrinos. This is the primary equation that I have only shown one, the Euler equation, the effective Euler equation of the neutrino fluid, where the neutrino has a sound speed, and then we can define a corresponding free streaming length associated with the sound speed. Because of this, in linear theory, neutrino basically suppresses the matter power spectrum and bispectrum by this amount, 8 f nu and 13 f nu, where f nu is the neutrino mass fraction, and this is very established. Now here we want to go to the higher order correction to the this Euler equation and the continuity equations. So we define the Redshift bispectrum in Fourier space by this Fourier average of the delta 2, delta 1 and delta 1. Okay. So the bispectrum is defined in terms of k1, mu and t. And the tree level bispectrum can be written like this, where f2 and g2 is the higher order kernel here. But these kernel are now neutrino corrected. Okay. So in this spherical harmonic, using this coordinate system, we can break this tree level bispectrum in in multipoles and define the corresponding reduced bispectrum multipole as well. So here we analyzed the various multipoles 0, 0 to 4 higher order multipoles as well, where this is basically allowed by the triangular inequality, where the bispectrums are we can get the signature, and this is basically the squeezed limit, and this is stressed limit, and this is equilateral limit. As you can see that in the squeezed and in the linear limit, linear triangle configuration, the neutrino signature are most prominent. And we also further checked whether this can be detected in Euclid-like galaxy survey, and for that we define a covariance matrix, okay, and between two multipoles Lm and L prime L1 prime, and for any realistic survey, we need to include the finger of God effect as well as the short noise, and we do include all of them, and we define the signal to noise ratio by this, the signal difference between the bispectrum also in presence and absence of neutrinos. And we obtain that in the stressed limit configuration, neutrinos we can detect with the neutrino signature with greater than 5 SNR in both 0, 0 and 2, 0 multipoles. And this is also true. However, in 2, 1 and 2, 2 multipoles, these signatures are strongest in the linear and squeezed limits. And once again, we can also detect this signature in 4, 0 and 4, 1 multipoles as well, but that needs to assess to more smaller scales, and that our theory doesn't allow, because that we have to go to the higher order correction for the bispectrum all loop corrected. So in summary, basically we saw that neutrino corrected bispectral multipoles, there in real space, there is a negligible effect, less than 0.1%. That's why we analyze the Redshift space enhancement, and we obtain that it has a 1 to 2% effect for neutrino mass 0.12 electron volt, and various multiple moments can be detected with greater than 1 sigma, greater than 1 SNR for Euclid light galaxy survey. So that's all. Thank you.
Okay, thank you, Saurabh. Yes, questions? All go.
So when you do the calculations, are you looking at the full matter power spectrum and bispectrum, or are you looking at the CDM part only of the matter power spectrum and bispectrum?
No, we're not looking at the matter bispectrum, first of all. We're looking actually the galaxy power spectrum.
Right, so that is only the CDM part.
Right,
so
CDM plus
that
CDM.
suppression is actually not 8 F nu in the power spectrum, that's 6 F nu. So
Yeah.
that
That's,
should be
yeah. That is basically, this suppression is basically the total matter power spectrum suppression. This is not CDM.
Yeah, in your multiple moment plots, I saw there are some white spots. Yeah, but later when you were showing, why it look distorted? Because
It's actually shown for greater than 1 SNR only.
okay. So the white part is not detectable. Okay, fine.